So welcome back, everyone. And, we are very happy to have Luca Iliesiu from UC Berkeley, and he's one of the recipients of the Frontier of Science Award. And let's welcome him.
Great. Thank you very much. Thank you very much for the invitation and for the very lovely week. So initially, I was thinking of telling you about the latest developments in near-extremal black holes. That's the reason why I was awarded this prize. But I hesitated because many of you have already heard about it, and I wanted to convey my excitement about some recent results. On the other hand, I see a lot of students around, so I wanted, if you're interested, to recommend a set of lectures on near-extremal black holes. And if you're interested in the actual latest developments, there's also a talk that I gave at KIPP about how near-extremal black holes evaporate and why quantum effects are important in their evaporation. And the paper should be coming out soon. But today I want to tell you about something slightly different. Namely, this morning we've heard from Roberto a lot about the Hilbert space of black hole macro states. One thing that Roberto conveyed very nicely is that now we have the ability to count that Hilbert space by using statistics. And what I want to convey in this talk is that we have the ability to also analyze the structure of that Hilbert space by using statistics. And namely, we'll be able to understand how the Hilbert space of two-sided black hole factorizes by using non-perturbative corrections to the gravitational path integral. And this is work that I've done with my grad students, Jan Boru and Gwanda Lin, and as well with Cynthia Yan, who's a grad student at Stanford. Okay, so let me start by posing the puzzle that we're trying to resolve. This is the so-called factorisation puzzle that's phrased in the setting of two-sided eternal black holes. So consider the Hilbert space of two-sided black holes. Here's the Penrose diagram of the black hole. And we can consider a slice specified by a certain gauge condition and analyze what the Hilbert space of the metric and matter perturbations are in this theory. And according to ADS-CFT and dr equals EPR, this Hilbert space should be described by a tensor product between a left Hilbert space and a right Hilbert space. But that's not actually what we get if we try to analyze this Hilbert space perturbatively. If we try to analyze this Hilbert space perturbatively, we get some sort of direct tensor product between a gravitational Hilbert space and a matter Hilbert space. And I'll be more accurate in the slide. So the factorization puzzle is that naively these two Hilbert spaces don't agree. So just to give you a model in which we can phrase this very concretely, I'll describe what happens in 2D JT gravity coupled to matter, which is the model that Subir and Alexei introduced earlier in the week. So this is a model in which the space-time is described by rigid ADS2 with a fluctuating boundary and fluctuating matter fields that could live on any slice. So let's say we pick some slice that's specified by some gauge fixing condition. So for instance, we could choose a gauge fixing condition that says we're focusing on geodesic slices. And we could ask what the Hilbert space of states living on this geodesic slices is. It's characterized by this tensor product between L2 of R and the matter Hilbert space, where this L2 of R describes the possible length that the geodesic takes when it goes between the two sides. Now, H matter itself, because we're in ADS2, the matter fields transform under irreducible representations of the universal cover of SL2R. So H matter can be decomposed into the unitary representations of this group, which are labeled by the eigenvalue of the Casimir, delta, and some states which are the eigenvalues of the operator L0 in SL2R. And this can take an infinite set of discrete values. So here we describe the Hilbert space in one basis, but we can trade this for a bunch of different choices. For instance, instead of describing this Hilbert space in terms of the length, we can describe the Hilbert space in terms of the left energy, right energy, and the Casimir eigenvalue, so the representation of the matter wave function on that slice. Importantly, the gauge constraint tells us that we cannot describe the wave function in terms of E left, E right, and an arbitrary matter wave function. We can only specify delta instead of delta and m. So it's always described by free numbers. Or we can imagine that we can prepare the state at an asymptotic boundary, and instead of describing things in terms of the left and right energies, we can describe things in terms of the left and right inverse temperatures. So there's all these different bases perturbatively, they're all equivalent. And what they have in common is that this is not a factorized Hilbert space between left and right. So for instance, here we have a left Hamiltonian and a right Hamiltonian that act on these two labels, but there's also an additional operator which acts non-trivially on the Hilbert space, which is what this value of delta captures. So the fact that the Hilbert space of two-sided black holes seems different than the factorized boundary Hilbert space is what's known as the factorization puzzle, and it was introduced in this series of papers. And these series of papers have, and I think it was common lore, that it was often thought that resolving these puzzles requires detailed knowledge about the UV completion of the theory. And I think what I want to convey today is that there is a possible resolution to this puzzle, and namely, it does not require the full knowledge about the UV completion. It only requires knowledge about non-perturbative correction in the gravitational path integral to see that H bulk truly factorizes into H left times H right when non-perturbative effects are included. And just because I've received this question before, and for someone that just hears the talk in our community might confuse these two puzzles, I want to emphasize that this factorization puzzle that I'll denote with an S is different than the factorization puzzle that I'll denote with a Z, that talks about the factorization of multi-boundary observables. So this factorization puzzle is about the Hilbert space of the theory. And this factorization puzzle says that if you look at the gravitational path integral with multiple boundaries, you can obtain different answers than by squaring the path integral with one boundary. And in fact, what we'll see is that the same wormholes that lead to this factorization puzzle are the ones that we use to resolve, this puzzle. Okay. So let me describe another way to talk about the lack of factorization, which is in terms of the algebraic classification of gravitational observables. So suppose that I look at the two-sided black hole, and I look at the left subregion, and I ask it, what is the algebra of observables in the left subregion? Well, we can do various degrees of approximation. First degree of approximation is that we're just studying a QFT in a fixed curved spacetime in a fixed background. So that's like turning off G Newton completely. So if I discuss a QFT in a fixed curved background, and then I describe the algebra of observables in a subregion, this is a type-free von Neumann algebras. And the problem with a type-free von Neumann algebra is that familiar notions cannot be defined. So notions such as trace, density matrices, pure states, or entropies actually aren't well defined on the subregion. So it's actually even hard to talk about the von Neumann entropy of the subregion. Things are actually a lot better once we impose the gravitational constraint. And typically, and Edward did a lot of work on this in the past couple of years, typically we see a transition from a type-free algebra to a type-2 algebra. So the advantage of a type-2 algebra is that once we couple things to gravity, familiar notions become somewhat better defined. So density matrices are well defined. traces are defined up to an overall multiplicative ambiguity, and differences of entropies are well defined. However, there is still no notion of a pure state. So somewhat amazingly, once we introduce gravity, notions that we're used to describe the quantum thermodynamic properties of a black hole become better defined, but we still haven't reached the point where we agree with what ADS-CFT predicts. So according to ADS-CFT, and this can be viewed as the finite G-Newton limit or the non-zero G-Newton limit, traces, density matrices, pure states, entropies are all well defined on one side of the system, which makes the algebra type 1. And in some sense, the fact that the algebra is type 1 and is well defined is equivalent to the fact that the Hilbert space factorizes between left and right. Once it factorizes, we can define a pure state, and once we can define a pure state, we have a minimal projector, which means that the algebra is type 1. Okay. A secondary outcome of addressing the factorization puzzle is an understanding how the algebra goes from type 2 once the gravitational constraint is introduced to type 1 once non-perturbative effects are included. And I think understanding how the algebra is type 1 is kind of at the core of understanding holography. Yes? No, probably not, but I don't know how to prove that. Maybe we can discuss that after the talk. Okay. So what is the actual strategy for solving this problem? The actual strategy is to start with a trace that we know is well defined. So that's the trace in the two-sided Hilbert space. The two-sided Hilbert space covers the entire region and has pure states. The trace is well defined. And discuss the trace for two-sided operators, for a product of two one-sided operators, one from the left and one from the right, and prove that for any operator in the left and right algebra, this trace factorizes into a product of two traces, one on the left and one on the right. So in this talk, we will mostly focus for simplicity on setting k left to be the Euclidean time evolution operator with Hamiltonian h left, and k right to be e to the minus beta right h right, in which case the factorization problem becomes showing that this trace is a function of beta left times a function of beta right. And if the eigenvalues of the left and right Hamiltonian are non-degenerate, this is actually sufficient in showing that the Hilbert space factorizes. But in principle, we can address whether or not this is true for a larger set of operators. Okay. So to even start defining this problem, I have to tell you what is H bulk. That was on the left-hand side of the equality. So to have a hope to see factorization, we need to break the gauge constraint that H left is equal to H right in a two-sided black hole. And if I only have pure gravity, I cannot do that. So for instance, if I prepare a pure, like the standard eternal traversable wormhole, that would have the left energy equal to the right energy automatically at any temperature. So to break the gauge constraint, you actually need matter fields in your low energy effective theory. And we'll assume that that's why we assume that our gravitational theory is coupled to matter. And we'll define H bulk as a function of some number k as the span of states in which I do some Euclidean evolution to the left and right of some operator insertion OI. And then just for simplicity, I can consider this state to be projected in some interval where the left and right energy belong to some arbitrary energy interval E. The purpose of this projection is just to make sure that we're talking about the finite dimensional Hilbert space instead of an infinite dimensional Hilbert space and as we shall see, we will also be able to track more easily when factorization happens. And I'll assume that I have some set of operators OI that are labeled from 1 to k. And while in principle, we can do this for operators with any scaling dimension, so for any SL2 representations, for simplicity and just to show you the calculations, I'll take delta 1 to be approximated by delta 2 to be approximately delta k. But in principle, we could do this with any deltas. And I'll comment on that later in the talk. And these are very similar, these states are very similar to the bag of gold states that Roberto talked about in the morning. In higher dimensions, these OIs would be exactly like the dust shells that Roberto talked about. Okay, so just like Roberto calculated the statistics of the dimension of this Hilbert space, I want to compute the statistics of this trace. So in general, since I can define pure states on the two-sided for two-sided black holes, the trace has a unique definition in terms of the states in H bulk of K. So if Qi and Qj would be orthogonal to each other, this would just be the standard formula for the trace in which I sum over the diagonal elements of this matrix. If Qi and Qj are not exactly orthogonal or not orthogonal to each other, this is a generalization of the formula for the trace, where I have to include the inverse of this Gram matrix of overlaps between different states in H bulk of K. So while we might not know these inner products or these matrix elements exactly, I think we now believe that we can compute their statistics using the gravitational path integral. So the philosophy here is that, for instance, if I want to compute the statistics of this overlap squared, I prepare the boundary conditions corresponding to Qi. I glue it to the boundary condition corresponding to Qj. I do the same for the other copy of the inner product. And I draw all possible connections in the bulk. So the leading contribution will be given by just the standard black hole geometry. In 2D, it's the geometry is a homotopic to two disks. But there's also cylindrical contributions and further subleading contributions. And I want to emphasize a little bit, this is just my philosophical perspective, that I think in the gravitational path integral, it's not necessarily to talk about an ensemble, but maybe we can view this answer for the average that the gravitational path integral gives you as a coarse graining of a regular UV complete theory, where we're coarse graining over the energy levels and OP coefficients that are chaotic. So from now on, whenever I put a bar, I'll denote that as the statistics computed from the gravitational path integral. So let's go back to the trace. So using these assumptions, we can, for instance, compute the trace of H bulk as the limit when n goes to -1 of this product of Gram matrices times this matrix element of e to the minus beta left H left, e to the minus beta right H right. It's just defined in terms of the pure states in H bulk. It's defined by this equation. This is a true equation. If I give you a Hilbert space that for which you choose some basis of states, so you have the span of some states, this is a true equation. So this is just the definition of the trace in terms of inner products in the boundary, if you want. And here I'm just giving you how to compute the statistics of this trace using the rules of the gravitational path integral. Okay, so how do we actually go from statistics to proving factorization? If we only prove that the trace factorizes on average, well, it's nice, but it's not an actual proof that the Hilbert space, the underlying Hilbert space factorizes. So we'll do this in 4 steps. So step 0 is to prove that indeed the trace approximately factorizes, meaning that it factorizes to leading order in e to the s naught or e to the 1 over g Newton. So we'll show that trace of H bulk of k left, k right is a product of traces for any beta left and beta right when k is bigger than the dimension of the Hilbert space. This is the exact dimension of the Hilbert space that Roberto computed. So it's when H bulk, the rank of the gram matrix saturates, and the states in the that I defined in the span to take the span of start becoming an overcomplete basis. So when that happens, the trace exactly factorizes. And when that doesn't happen, we get a complicated non-factorizing answer. So I'll show you the formula later, but this is also consistent with what we expect from the boundary. If we define some Hilbert space that doesn't span the full bulk Hilbert space, disagrees with it, we shouldn't see a factorizing answer. But once the two Hilbert spaces agree, we should see that factorization is resolved. So this is an approximate statement. But then what we can do is go to subleading orders in the e to the 1 over g expansion by considering further non-perturbative corrections in the gravitational path integral. So this answer already is obtained by considering complicated wormhole corrections. This answer is obtained by considering higher genus wormhole corrections on top of the wormholes that we considered previously. So what we'll find is that trace H bulk, which for simplicity, I'll denote as Z bulk of beta left, beta right, is no longer actually a product of a function of beta left times a function of beta right, but the average of trace H left times trace H right, where this average is captured exactly by the computation in which I'm allowed to connect the left and right boundary when computing the trace using the Gibbons-Hocking description. So seemingly this seems bad because Z bulk is no longer a product of a function of beta left times a function of beta right. But this is actually consistent if I take a set of theories in which each one of them factorizes, and I compute Z bulk of beta left, beta right in each of them, and then I average them. I shouldn't expect to get an exact product of a function of beta left times a function of beta right. I should only expect to get that at leading order. So to really probe factorization, we need to find an observable that directly probes it before coarse graining. So to do that, we can define the following differential that simply tests whether a function is a product of two functions. So this differential with respect to d beta left and with respect to beta left and beta right tests whether or not Z bulk of beta left, beta right is a function of beta left times a function of beta right. It's obtained, if you want to get an intuition for how it's obtained, we can take the log of Z bulk. The log of Z bulk, if Z bulk is a product, should be a sum of a function of beta left plus a function of beta right. And to that log, you can apply d beta left to d beta right, and that should vanish. Rewriting that log gives you this slightly more complicated expression. So proving that d beta left, d beta right is 0 is equivalent to showing that the Hilbert space factorizes into H left times H right if we assume that the eigenenergies of the left and right Hamiltonians are non-degenerate. And I'll actually discuss what happens if they're not slightly later. So step 2 of proving factorization is to show that to all orders in the non-perturbative expansion, D vanishes on average. And step 3 is to also show that D squared vanishes on average. If we show these two, then it means that D is exactly 0 before coarse graining. It's 0 either in each member of the ensemble or before I did any sort of coarse graining over energy levels or OB coefficient. So this is what we will show. Any questions? We can check it for any power, but this is sufficient, right? If you show that for the average of a real number of a distribution is 0, and you show that the average squared is 0, it's sufficient to show that it vanishes exactly. Okay. So So let me start by spending more time on step 0 because I think that's the one that physically is most relevant, actually. So proving factorization to leading order in 1/G requires the following double scaling limit, which simply will tell us that we will want to study the Hilbert space H bulk of K as it approaches the non-perturbative Hilbert space in the bulk. So we'll take K to infinity, the number of states in our Hilbert space, to be very large. We'll take e to the s naught to infinity, which consequently means that the expected dimension of the Hilbert space from the Gibbons-Hawking prescription is also very large. And we will take k over d squared to be order 1. Okay. So within this limit, what are the statistics of the trace? Well, just naively writing the possible contributions to this product of inner products, I have to prepare n boundaries, each one associated, or n plus 1 boundaries, each one associated to this inner product, with one of the boundaries having the insertion of k left and k right, which is the boundary that's associated to evaluating this matrix element. And then I have to sum over all possible operator insertions, which is like summing over all possible states in the contraction. Good. So the leading geometry in e to the s naught is purely the disk geometry. And this is what we would get if we only did a perturbative analysis. So what do we get if we only keep disks? Well, you can evaluate each term independently, and if you say that all scaling dimensions of all operators are approximately equal, you get an answer that it just keeps growing with k. That's just because the dimension of the Hilbert space keeps growing as we put more and more states in H bulk of k. And consequently, if you study the differential d of beta left, it should be a beta, d of beta left, beta right, you also get an answer that grows with k, you will never get 0. So therefore, perturbatively, we will never see that the Hilbert space factorizes. And the mistake that we've made is that when k is of order d squared, we cannot ignore subleading contributions in e to the minus s naught. And this is something that people know very well nowadays from studying the page curve in these models. So we can see this very simply by also putting factors of k here. So the contribution of these geometries goes like k times e to the 4s naught. But here, there's more in the blue lines represent the sum over possible matter indices. Here, there's more cycles for the matter indices, so there's a higher power of k. So I should compare k times e to the 4s naught to k to the 4 times e to the minus 2s naught, and the two are comparable in the limit in which k over e to the 2s naught is order 1. So I should include both of them. And now the simple question is, how do we resum all such geometries? Because I can consider more complicated connections between these different boundaries, and they will all contribute at exactly the same order. And this was first done in the paper of Pennington, Schenker, Stanford, and Yang. And we studied a generalization that was more similar to this setup, in which we just couple JT gravity to ordinary matter. So to resum all such geometries, we can define a resolvent for the matrix of overlaps. So this is very similar to the resolvent that Roberto defined this morning. So it's defined as 1 over lambda minus the Gram matrix of overlaps. And the nice thing is, one computes the resolvent, one can easily compute the trace that we're interested in, because the resolvent allows us to write the matrix M inverse very easily using a contour integral. So we have to compute the resolvent times this matrix element. And here, if you actually track what we need in order to compute the trace, what contour computes the trace, it's the contour that surrounds all possible non-analyticities of the resolvent. So the non-analyticities, or poles or branch cut of the resolvent, signal the fact that M has an eigenvalue that is taking that value. So the possible eigenvalues of M are either along the positive real line, or they can be at 0. And as I'll show you in a couple of slides, the eigenvalue at 0 turns out to be critical. Okay, so since there are a lot of students, let me very briefly review how to obtain what's called a Swinger-Dyson equation for this resolvent by expanding the previous formula, this one, in a geometric series. So in a geometric series, you end up with a product of inner products that are multiplied by different powers of 1 over lambda. And when I am interested in computing the average of the resolvent, for each inner product, I can consider any possible bulk geometry to fill it. So at order 1 over lambda, there is no boundary, there's no asymptotic boundary that's created by an inner product because there's no inner product. At the power 1 over lambda squared, there's one inner product, so there's one asymptotic boundary, and so on and so forth. So the possible geometries at this leading order that I'm studying is a disk at order 1 over lambda squared, and at order 1 over lambda cubed, now I have 2 disks and a cylinder. And just like I emphasized in the analysis previously, this 2 disks and cylinder actually contribute at the same order because of the competition between k and e to the 2s naught that occurs in the double scaling limit. So I have to sum over all of them. And to sum over all of them, it's very convenient to rewrite the resolvent as a sum over a quantity that involves resolvents itself. So this is a schematic way of getting the, if you look at all the possible geometries that contributed in the previous slide and go to higher and higher order, you could insert the resolvent itself in the expansion, and you get the Swinger-Dyson equation where on the left you have the resolvent, and on the right, between any 2 operator insertions, you could also insert a resolvent. And moreover, since we're interested in the trace, we can also express the trace itself, the product between the resolvent and this matrix element, also as a sum over a simple wormhole with a lot of resolvent insertions. But now this wormhole, as compared to the one in the standard Swinger-Dyson equation, has a k left and k right inserted. Okay, so let me write an actual formula for the actual Swinger-Dyson formula that's associated to those pictures. So for the resolvent itself, it takes this form, where these functions y capture the correlators on these pinwheel geometries, on these multi-boundary wormhole geometries. So this is just O delta here is just the operator. Yeah, it's the matrix element of the operator in the eigenenergy basis with energies S left and S right. And notice that this formula is quite complicated. It has R of lambda both on the left and inside of the integral on the right. So it's a complicated integral equation that cannot be solved analytically, or at least I don't know a solution. And if we don't solve it analytically, then it might be difficult to compute the formula for the trace, because the formula for the trace also has the resolvent inside of a contour integral on the right-hand side, where the function yk is now given by the correlator on the wormhole in which k left and k right were inserted. So it's the same function here, but multiplied by this additional factor of e to the minus beta left and e to the minus beta right, which capture the left and right Euclidean evolution. Good. So while we cannot solve this analytically, it turns out that factorization occurs for a very simple reason. So let's take a closer look. So imagine that we're doing this contour integral over the resolvent that surrounds the possible non-analyticities of the resolvent. And when computing the trace, we can deform this contour integral, and we can show this vigorously, from this contour to the contour that just surrounds the origin, lambda equals 0, where the function that we're evaluating, that we're taking a contour integral of, has a pole that goes like 1 over lambda, regardless of whether or not the resolvent itself has a pole. So now we have this function that we want to study, and there are two possibilities. One possibility is that R of lambda is just smooth at the origin. It just takes the value R0, and if that happens, then this integral. So if that happens, then it means that the overlaps Qi, Qj are not degenerate. So the Gram matrix hasn't achieved maximal rank, right? When the Gram matrix has a 0 eigenvalue, it means that we're studying a basis that's overcomplete. So if we don't have a 0 eigenvalue and therefore don't have a pole, it means that the basis is not overcomplete. So there's no linear combination of the states that vanishes. This is what we call that there are no null states. And if that happens, then we see by explicitly plugging in R of lambda equals R0, that we get to this very complicated expression that's a complete mess in the integral over E left and E right. And the only thing that I want to emphasize in this formula is that, of course, because this function that we're integrating doesn't factorize in terms of E left and E right, the final answer won't factorize as a function of beta left and beta right. So we get an ugly non-factorizing answer. But once null states exist and R of lambda has a residue, then this contour integral simply gives the ratio between these two functions. And this is exactly the ratio between the correlator evaluated the wormhole with the k left, k right insertion and the wormhole without the k left, k right insertion. So this ratio simply evaluates to e to the minus beta left, e left, e to the minus beta right, e right, and therefore we get a factorizing answer. So the mechanism for factorization is highly linked to the fact that there exists a pole at the origin, which means that within the Hilbert space H bulk of K, there are null states, which signify that linear combinations of those states become redundant. So null states imply factorization. So to complete our discussion, we simply need to study the analytic structure of the resolvent. And number one, check whether the contour deformation that I said is valid. Number two, we should understand when a pole appears at the origin. So yeah, so when you take the limit n goes to -1, the contour that you end up surrounding is the one along the positive axis. And then you deform it back to lambda equals 0, essentially. And then you prove that the deformation is valid by showing that there's no contours and contributions at it. Yeah, so the case when k is exactly equal to d squared is a bit more subtle. We can discuss the case when k is bigger than d squared or k smaller than d squared, in which the case the non-analyticity on the real line does not hit lambda equals 0. But we can even understand the case when k is equal to d squared. Yeah, maybe let me just say what we proved. Yes, yes, but if you consider k just bigger than d squared slightly, you no longer run into that problem. So it's only when k is exactly equal to d squared. But we can see exactly what happens. So when we get that the resolvent has a step function that only activates when k is bigger than d squared. This can be seen by taking this ansatz and putting it back in the Swinger-Dyson equation and showing that it actually solves the Swinger-Dyson equation. So this essentially R of lambda only has a pole when k is bigger than d squared, which is exactly what we expect. We can only have null states once the full Hilbert space is spanned. And the residue simply gives the number of null states. So the number of null states is the naive dimension of the Hilbert space minus the real dimension of the Hilbert space. related to what Jimbin said, we can also study what happens to the finite part of R of lambda, or the value of R of lambda that R of lambda takes when k is smaller than d squared, and itself starts diverging when k is equal to d squared. So what happens is that the finite value R of lambda is finite up to k equals d squared, and all of a sudden it develops a pole at k equals d squared, at which pole that pole becomes this 1 over lambda pole that you see in point 1. And this value of R0 will help us understand how we're approaching a factorizing answer as k goes to d squared. And finally, we checked that there are no other non-analyticities appearing on the negative real axis. So this is actually an important check, because this is a way to show that we've defined a good inner product, even non-perturbatively, meaning that the inner product is positive semi-definite. So one can simply quotient the null states out of the full Hilbert spacing, of the full vector space, and with this inner product get a well-defined Hilbert space. Okay, so therefore we can track what trace of H bulk is as a function of k. You could view this as an analog of the page curve for the Hilbert space factorization. So when k is smaller than d squared, as I said, that resolvent is complicated to compute analytically, but we can compute its value numerically and obtain what the trace is. And we see that it keeps growing as a function of k up to the point when k is equal to d squared, at which point it saturates exactly at the value of trace left times trace right, where the densities of states are predicted by the Gibbons-Hawking prescription. And this red curve is from the previous slide. Remember that we computed the behavior of the resolvent as k approaches d squared. So this tells us how this analytically tells us how we're approaching a factorizing answer, and it's consistent with the numerics that we computed. The fact that we don't get factorization when k is smaller than d squared is a sign that it's not a guaranteed property by diagrammatics. You actually have to resum all the diagrams in order to see that the trace factorizes, and it only occurs for starting at a specific value of k. Okay, so we can also compute the differential to leading order in 1 over g Newton, just using the property that at leading order, the product of z bulk simply obtains contributions from fully disconnected geometries. If I had handles connecting any one of these two, they would be suppressed by e to the minus s naught, but have the same power of k. So even in this double scaling limit, we only get contributions from disconnected geometries. So in other words, z bulk of beta left, beta right is self-averaging. So from the value of z bulk that I wrote down, we can easily compute what d is. So here I'm plotting log of 1 plus d versus log of k. And you see that the differential initially is growing just because I'm adding more and more states to my Hilbert space. Remember that the initial prediction, the perturbative prediction, was that the differential grows linearly, and that's what we're seeing. And we're seeing that for any value of beta left and beta right, the differential becomes exactly 0 when k hits d squared. Okay, so let me make a few observations before moving to step 1 through 3. All the wormholes that are discussed are actually saddles at large enough delta. And the fact that they're saddles in 2 dimensions means that they typically have a generalization in higher dimensions. So for instance, the wormholes that shell wormholes, the dust shell wormholes that Roberto discussed are generalizations of these wormholes and can probably be used to prove factorization to leading order in 1 over g Newton in higher dimensions as well. And finally, we can check that factorization and the dimension of the Hilbert space, the fact that a Hilbert space factorizes in its dimension, is completely basis independent. This is just a consistency check. So if instead of generating h bulk of k using an asymptotic boundary, I simply describe h bulk of k in terms of geodesics and the matter wave function on geodesics with arbitrary delta I and mi, I can use the statistics of the inner product to show that the moment when factorization occurs is exactly the same as for h bulk of k defined by a different basis. Finally, the resolvent itself can be viewed as a projector in the Hilbert space, and this is going to be very useful for the computations to follow. So I can write trace k left and k right as the expectation value in a thermal field double state with inverse temperature beta left and one with inverse temperature beta right of some operator O hat. By cutting all the pinwheel geometries that I show along a green geodesic that separates the pinwheels from whatever segment along which I insert k left and k right. So I can essentially completely cut out the k left, k right insertion. And one can show that the results that I showed you previously imply that this O hat is actually a projector onto an infinite temperature state. So they're just the integral over d left with d right with beta left and beta right equals 0. So if I glue this to any beta left, beta right, I'll get a factorizing answer when k is greater than d squared. So this is just an observation, but the actual numerical expression, the value of the operator for this cutout pinwheel geometry will actually be very useful to discussing what happens when I allow these wormholes to have an even higher genus, to have a higher genus. Yeah, so imagine here that the integral is restricted over some energies, and then you get the infinite temperature states within that energy. Okay, so now we would like to go beyond leading order in 1 over g Newton and include higher genus corrections. So for that, we have to compute the product of the resolvent and this matrix elements when we include further handles on the wormholes. And the handles can, be either on one side of this pinwheel, can connect to the other side, or these geodesics can wind around these additional handles, so on and so forth. So these geometries all contribute, but geometries that have a non-planar index contraction for the contraction of the indices of operators are actually suppressed in K. So if we're taking the limit K to infinity first, this set of geometries is actually sufficient for studying the statistics of the trace. So in this part of the talk from now on, I'll take K to infinity faster than I'm taking e to the s naught to infinity. And this is just to give you some intuition. This is just to suppress some statistical fluctuations in the size of the Hilbert space. Yeah, so these are not on shell anymore. The previous ones were on shell. These are not on shell. And on all these wormholes, we can perform the following decompositions in which we always cut any handle component of these wormholes along by using a green geodesic that is homotopic to the union between the red segments and the black segments of the pinwheel. And because there is a unique such geodesic, there's a unique green geodesic that has this property, this cut is specified in a unique fashion. So there's actually no mapping class group ambiguity when we discuss these sorts of cuts. So this allows us to separate our wormholes into the familiar component, the cutout pinwheel, and a new component that kind of looks like the wormholes that we've been discussing in the literature in the past couple of years that have two asymptotic Euclidean boundaries connected by handles. The only difference is that these boundaries consist of an asymptotic segment and the geodesic segment. The green is just geodesic. So using that, we can write trace of h bulk as being obtained by this gluing along this left and right geodesic, in which we glue these wave functions, phi beta L and phi beta right. This is phi beta left, phi beta right, times the operator that I obtained previously that captures the cutout pinwheel. So because I know what the value of the operator is from previously, it's just the wave function, in the infinite temperature limit for the segmental left times the wave function in the infinite temperature limit for the segmental right. Plugging that in, you find that this answer, using the fact that this depends on the spectral correlator of rho, you find that the answer for trace bulk agrees with the answer for the average of two traces, where the average of two traces is defined in terms of the rho correlator given by these types of wormholes that I discussed previously. So the fact that I could use this expression for O left, O L left, L right, this is only valid if I take k bigger than d squared. But since I'm considering the limit when k is much bigger than d squared, of course I could use that value of O left, O L left, L right. So this answer that we obtained is consistent with factorization before CRISP grading. But as I said at the beginning, we want to probe factorization even more directly. So as I said, we'll look at this differential operator. Sorry, at this differential that can be defined in terms of this differential operator acting on the product of two z bulks when setting beta left equal to beta left prime and beta right equal to beta right prime. So in order to compute that, we have to compute the average of a product of z bulks. But we can use the same trick as before. So now I have to sum over all possible connections between all these geometries. But I can always cut these connections out using the geodesic cuts that I was using before. And you get an expression of this type in which you get the operator associated to two cutout pinwheels and an answer that's captured by the statistics of four of these wave functions that in which I have an asymptotic segment of length beta left and some geodesic segments. So this could have any possible wormhole connections between the four patches. So gluing everything together, we just get that the product of two z bulks is given by the product of rho. Now, rho, which is the spectral correlator of four energies, is symmetric under the energy exchange of any of two energies. In particular, it's symmetric under the energy exchange of E left and E left prime. So when I fix beta left equal to beta right and beta left equal to beta left prime and beta right equal to beta right prime, since this differential is anti-symmetric in these quantities, you could easily show that the average of D is 0. And you can now repeat a similar decomposition for an arbitrary product of traces. And you could show that an arbitrary product of traces, averaged, simply depends on the average spectral correlator with 2n insertions of rho, where we perform these 2n integrals over the energies weighted by their Boltzmann weights. And again, using the fact that this spectral correlator is symmetric under exchanges of E left and E right, when I act with the differential operator and set beta left I equal to beta right I, you could see very easily that the differential operator to any power vanishes. In particular, the average of d squared is 0. And this is actually a very general argument that didn't actually rely on what the value of these off-shell wormhole was. It only relied on the properties under symmetry exchange of E left, E right. So famously, there's a problem with these wormholes, these offshore wormholes in a matter theory, which is that they have a matter divergence for small wormhole lengths. But even in the presence of such a matter divergence, you could imagine regularizing it. Even if you regularize it, you would imagine that the statistics of a product of spectral correlator, sorry, of a product of rows is symmetric, is still symmetric under energy exchange. So we expect this property to be true even if we talked about a theory in which this divergence gets regularized. Intersect with my O operators. Maybe we can talk about that afterwards, but I don't think that there are cycles that have that property along which the divergence occurs. So, oh, yes. You mean the fact that even here, when I consider the on-shell geometry, there is, even in the first derivation, there is a problem that if I go very much off-shell, I have a contribution from the divergence. Yes, I agree with that. In any case, despite only having access to statistics, we can prove that a factorization occurs before first graining by showing that the average of this differential is 0 and that its standard deviation is 0. We showed this at very large K. But that doesn't really matter because the Hilbert space at the end of the day should be the same if I make K very large. We saw that its rank eventually saturates. So here we've shown to all non-perturbative orders that the differential vanishes regardless of what beta left and beta right are, which is what I consider to be showing that factorization occurs. So let me make some final comments. So let me go back to the problem of trying to show that the algebra of one side is type 1. I think this follows pretty easily from the fact that on the left-hand side, we have a well-defined trace where the trace H bulk has pure states. Now imagine setting K left is equal to K right. This gives me an answer for a one-sided trace of some operator in the theory. The fact that this trace is well-defined, of course, implied that the one-sided trace is well-defined and doesn't have a multiplicative ambiguity. And that's a requirement for a type 1 algebra. So that's just a sanity check. The second point is that we can make a different choice of a Hilbert space. This is something that Whitten and Pennington did. And they found that when we include non-perturbative corrections, the algebra still remains type 2, not type 1, as we said. And it would be interesting to study more differences between these two choices of Hilbert spaces. The third point is that we assume that there are no degeneracies of the eigenenergies in our analysis. Of course, there are cases in which there are degeneracies. So for instance, what if there is a boundary global symmetry that has irreducible representations with dimension greater than 1? And this would correspond to a bulk gauge symmetry. Well, in that case, we can probe factorization in a more detailed fashion by not only introducing the Hamiltonian in our analysis of the two-sided trace, but also inserting chemical potentials. And if you prove that this function is a tensor product of a function of beta left and alpha left times a function of beta right, alpha right, that is sufficient to show factorization. So one point, though, is that to even define H bulk, we need to break the gauge constraint not only between the left and right Hamiltonian, but also between the left and right charges. So this actually requires that we add the particles OI that we use to define the Hilbert space H bulk can live in all irreducible representations of the gauge group. And this is essentially what the completeness conjecture claims. And this analysis is somewhat similar to Harlow's analysis from 2016 that used the Wilson line between the two sides of the black hole to say that these sort of particles are necessary in order for the Hilbert space to factorize. And I wonder if one can find further constraints on the matter content of the gravitational EFT using similar principles of requiring factorization. We haven't found any so far, but I encourage you to also look. The fourth point is that there are some exceptions of having degeneracies that cannot be split by bosonic charges. For example, BPS states cannot be split by adding a chemical potential for the R symmetry charge. So in that case, we need to use other operators to prove factorization. And we actually did this in the paper where we consider k left and k right to be the exponential of a simple operator that's projected onto the BPS sector. So we consider two-sided BPS black holes in which we insert these operators, k left, k right. And we can prove that this factorization statement where this trace H bulk is now the bulk Hilbert space, the two-sided bulk Hilbert space of BPS states, we can prove that this factorization occurs exactly when k is greater than dBPS squared. We actually don't need to take k to infinity to suppress statistical fluctuation. And if you're interested, I can tell you more about that. The fifth point is that we have a lot of null states. We have tons and tons of null states. There's linear, we started out with a Hilbert space that had labeled E left, E right, and delta, or L delta and M. And we ended up with a Hilbert space that only has two labels, the left and right energies that are now discrete because the Hilbert space is finite dimensional. The fact that you could write even a pure state as a linear combination of these states, of course, shows that there is no linear operator that measures the connectedness of the space-time. This was a point made by Daniel Jaffrus, but I think it fits nicely in our story. And also the length, if one tries to define a length operator, it stops having a geometric meaning in this Hilbert space H bulk of K. One reason why is because I can actually show that you could write absolutely any state in the Hilbert space as a linear combination of states that have the same geodesic length, which is kind of funny, a funny feature. What does L even mean in that case? This geodesic length has been recently used to probe various properties of for an infilling observers. And I guess the question is, given all these null states present in the theory, what does this tell us about the experience of an infilling observer? The sixth comment is that step 0 only involves saddle points in the Euclidean path integral, so it can be generalized. Steps 2 and 3 involve general symmetry arguments about the spectral correlator of the theory, so perhaps that can be generalized to higher dimensions as well. The fact that we see that this differential exactly vanishes is very much a consistency check of the fact that wormholes probe some coarse graining in a tensor product of conventional quantum mechanical systems. Imagine if we didn't get that D is exactly 0. Then what could we have concluded about the contributions of wormholes in higher dimensions, where we know from construction that this Hilbert space of two-sided black holes should factorize? And finally, in all I've discussed, we've now understood that factorization can be seen directly from the bulk path integral. It didn't actually rely on boundary arguments. So I wonder if this can help us understand the structure of the Hilbert space for spacetimes that have cosmological horizons instead of having black hole horizons. Thank you very much.
In that situation, you don't expect it.
Yes, yes, but Yes, maybe the specific thought that I've had is whether or not one can show or one can understand whether the algebra in the of observables in the static patch eventually becomes type 1 if one includes non-perturbative effects in the gravitational path integral. I don't know the answer to that. I know that it goes from type 3 to becoming type 2, but I'm wondering whether there's a way of seeing that once you include non-perturbative effects, it goes to type 1, just like we did here.
Sounds like. Side space.
Yes, yes, I don't know.
Let's take the speaker again.